Hello all, welcome again. So in the previous class we were looking at this case study of reducing, silicon has this native oxide which prevents any sort of epitaxial growth. So we said let us reduce it, okay, and then start growing any sort of functional material on silicon, a thin film. Through one of these techniques, right. So it can be chemical vapor deposition, it can be pulse laser deposition, any of the physical vapor deposition techniques. But the fundamental point is you have to first remove, so while the deposition is happening, it is nice if there is no silicon oxide. I mean, only then there can be epitaxy, only then will these incoming atoms be able to see the crystal potential. Okay, so that is what we set up the problem. We said, okay, so let's try just etching the silicon oxide. Okay, we can do that, but once you etch the silicon oxide, the oxide again reforms within just instantaneously. Okay, so at whatever pressure you are, at all the achievable pressures inside a vacuum chamber, this is what happens. Okay, then the second strategy we said, okay, so let's try to look if we can go to high enough temperature such that then with playing with both temperature and pressure, reducing the partial pressure of oxygen, can we go to these reducing conditions? We have to reduce silicon oxide, right. So back to silicon. We tried that and we said, look, no, I mean, so I have to go to ridiculously large temperatures like 4000 degrees Celsius or something like that, and to be even at at the lower end of the pressures that my vacuum chambers can take, right. So this is also quite impractical solution. Okay. Then we said, all right, so something that just my vacuum chambers can do, my vacuum systems can do, so a chemical species do that, right. So a reactive chemical species, and the reactive chemical species, we took our inspiration from blast furnace, and we said I am going to put in some carbon monoxide and say let this carbon monoxide react with the oxygen of silicon, right, and form carbon dioxide. That way I can flush out both carbon monoxide and carbon dioxide from my chamber, and I get my silicon which is free of the native oxide, right, because the native oxide then reduces, right. Now that is a reasonably good strategy. It works beyond, so I need to have always I need to maintain this PCO by PCO2 which is at least greater than 10 power 6, that is what we have calculated. Using these two reactions in conjunction with each other, and then we said, okay, so if that is the case, that is an achievable thing, and that is what people do even in blast furnaces. And I can also use H2 gas. H2 also goes to H2O, and then lot of H2 and very little H2O. So if I keep maintaining that ratio, then so I can indeed reduce silicon oxide. So that is the second strategy. It is a strategy based on reactive gases. I can definitely employ it. It is not unemployable. But the issue is, so it will be nice if I do everything in sort of a solid state manner, right. Now, so that brings me to the third strategy to solve this issue of removing the native oxide layer, so that I can further grow my functional materials on this thing. Okay. Okay, so this actually comes down to if I look at delta G naught, right, versus T, let us say the delta G naught versus T of silicon is somewhere here. This is silicon plus oxygen gives rise to silicon oxide, okay, which means so above this we said we are in an so if my conditions are above this, right, so if my Q is such that the conditions are above this, or partial pressure of oxygen is larger than the value set by so whatever I am going to read off from this axis, then I have oxidation, and below this we said I can reduce, and going below this was an issue, right. So but this line sort of separates my oxidation from the reduction window. This we have seen in the earlier classes. Okay. Okay, fine, that is fine. So then so this is silicon plus oxygen gives rise to silicon oxide. So this is oxidation and this is reduction. right. But getting to the reduction conditions just by reducing the oxygen content is very hard, right. So, that is what we said. Okay. So, then alright. So, now if I take some other reaction, right. So, let us say titanium plus oxygen gives rise to titanium oxide is here, right. In this window, for example, this is oxidation for titanium, this is reduction for titanium, right. Now, I have a window here, and in this window silicon gets reduced, titanium gets oxidized, right. In fact, the delta G naught of titanium to get oxidized is much larger, right. So, if I look at let us say this Ellingham diagram, titanium plus oxygen giving rise to titanium oxide is here. So, the delta G naught is more negative, right. So, at any temperature I can look at the delta G naught is more negative, and that fundamentally means that I have more propensity to oxidize, right. So, I can oxidize even at lower partial pressures of oxygen, right, compared to silicon, right. So, silicon itself is instantly oxidizing, but titanium has more propensity to oxidize than silicon, that is what it means, right. So, if I am reading this correctly, I mean by now, right, I can look at the values of delta G naughts and then say that look, the delta the lower it is here, right. So, it has more propensity to oxidize, right. The higher it is, it has more propensity to reduce, right. So, which has a more oxidation potential, is it titanium or silicon? Just looking at this Ellingham diagram, I can say look, the delta G naught of silicon at any given temperature is silicon plus oxygen giving rise to silicon oxide at any given temperature is larger than the delta G naught of titanium, right, at any given temperature. So, titanium, if I put both of them together, titanium will oxidize first and silicon will start oxidizing next, okay. So, there is this window, for example, right. So, in this window titanium is getting oxidized, silicon is getting reduced, right. Similarly, I can also have aluminum. Aluminum has a huge oxidation potential. I have shown you earlier, right. So, aluminum actually takes away oxygen from lanthanum nickelate in this example, right. So, aluminum has a huge oxidation potential. I can use magnesium. Magnesium also has a huge oxidation potential. I can use calcium. Calcium also has a huge oxidation potential, or zirconium, which is not here, but zirconium is also somewhere, so it has a larger oxidation potential than silicon, okay. All right. So, I am going to use this fact now, right. So, now my reactive species is not a gas anymore, right. So, I am going to use the fact titanium has a greater propensity to oxidize than silicon, okay. In fact, titanium has so much of propensity to oxidize that in vacuum chambers, right, I can put in some titanium, so that this titanium is just going to absorb the oxygen, and that way I can even reduce the pressure inside the chamber just by putting some titanium. This is a very a ghetto way, I must say, but yeah, you can just put some titanium and you will see that the titanium has absorbed all the oxygen or lot of oxygen, and that so all your oxygen is in the titanium solid chunk that you have. So, there is not gaseous oxygen around floating around, right. So, because titanium has huge propensity to oxidize even at room temperature, right. So, this delta G naught tells me the driving force for titanium to oxidize even at room temperature, and this is huge, right. So, same thing with aluminum. Aluminum also, if I leave it in atmosphere, it will immediately get oxidized, right. So, and aluminum will get oxidized even faster than silicon will get oxidized, right. So, aluminum has much larger propensity to oxidize, right. So, when I say okay, so this has larger propensity for oxidation, this has lesser propensity for oxidation, the number that I will give you is delta G naught, I can always say delta G naught for aluminum to oxidize at room temperature is minus whatever 1000 kilojoule per mole, whereas for silicon it is just minus 500 kilojoule per mole, which means I know that both of them have propensity to oxidize, but aluminum more so than silicon, and this is what Ellingham diagrams say. Right. So I mean, there is a window where silicon is still getting reduced, but aluminum will get oxidized, and that translates into rates and other things. Okay, the rate of oxidation and things like that. Okay, and you have what are called titanium sublimators, which are also vacuum. So to create ultra high vacuum. So you sublimate titanium, and then that also picks up oxygen, and then so you don't have oxygen in the chamber anymore. And you can reduce the the pressure inside the chamber, right? So this is a well-known technology that I can use titanium to oxidize. Titanium gets oxidized, and at the cost of the oxygen that is already available, and so I can reduce pressures inside vacuum chambers. Okay, so that's known, right? But here what we are doing is we are using titanium to get out oxygen, titanium or aluminum or zirconium to scavenge oxygen from silicon oxide. Okay. Now, when I am scavenging oxygen from silicon oxide, so this is in a solid state, right. So, I am going to use the reaction titanium plus oxygen gives rise to titanium oxide, right. So, to take away the oxygen from silicon plus oxide gives rise to silicon oxide. So, this oxygen gets fed into this reaction. Again, this is reaction 2, this is reaction 1, this is the important reaction, this is what I want to happen, but I want the backward reaction to happen. Okay. So, as a result I need to give away this oxygen to titanium, right. So, or in other words, so from silicon oxide titanium takes away the oxygen and forms titanium oxide, right. So, I can combine them and write titanium plus silicon oxide gives rise to titanium oxide plus silicon, right. So, this is the reaction I am going to use. This is the compound reaction. Okay. So, now the question is simple, is this reaction feasible, right. So, and under what conditions is this reaction feasible, right. So, essentially this looks like it is possible because so earlier I have shown you that aluminum actually oxidizes by taking aluminum from lanthanum nickelate, right. So, in fact, if I write this more rigorously, right. So, this is a more reactive metal, right. So, titanium is a more reactive metal. So is zirconium, so is aluminum. So, I can use all these to reduce silicon, or in other words very intuitively I am saying that aluminum is going to take away the oxygen from silicon oxide and then give you silicon, right. So, reduce it to silicon, right. The issue is, however, I am forming titanium oxide here, this is solid state, right. I mean, it may not be an issue, but I am just pointing out, right. And this is different from carbon monoxide plus silicon oxide giving rise to carbon dioxide plus silicon, right. So, you can balance this equation plus silicon, there should be one extra oxygen, but yeah, so this one, right. So, this should work out, no, sorry. Anyway, so you can balance the reaction, it should not be that difficult. Now here so all my products, all my side products are still gaseous, so I can remove the gases, right, but solids are there to stay, right. Okay, so then the question is, all right, so let us say this works. So, instead of silicon oxide, then I am reducing it to silicon, but then I am forming titanium oxide. How does this work? Now, I am replacing one monster of silicon oxide with another monster, I will put monster in brackets, which is titanium oxide. Okay. Now, this works because titanium oxide crystallizes, right. Silicon oxide, to crystallize silicon oxide is very hard. Silicon oxide does not crystallize that easily. Okay. Whereas titanium oxide can exist in rutile phase or anatase phase, whatever, but then titanium oxide is known to crystallize. So, essentially I am replacing, through this reaction, I am replacing silicon oxide amorphous, and that is the important part, with titanium oxide crystal, right. So, I have now silicon, and I have, on silicon I have a titanium oxide, but this titanium oxide is also crystalline, right. Maybe slightly different crystal structure, but this will also try to take the crystal structure of silicon underneath because it is thin, right. And so, I have a crystalline potential, but this time the potential of titanium oxide, right. So, all these atoms have dangling bonds now, right. And on these dangling bonds I still, so my film is still able to see a crystalline potential and more or less defined by silicon, right, because this is also thin enough. This sees the crystalline potential of silicon, that is transferred here. The crystalline potential of silicon is transferred onto titanium oxide, and so the film also sees the crystalline potential of titanium oxide in practice, but then titanium oxide itself is seeing the crystalline potential of silicon, right. So, the silicon crystalline potential is transferred to titanium oxide. Is transferred to titanium oxide, and that is transferred to the film, right. So, this is a pretty nice thing. Okay. So, in fact, you can see that this works, right. So, I will just show you quick examples, and before solving a problem, so do I have something here? Yes. So, for example, look, so this is silicon, right, and then we put in some zirconium and hafnium. I mean, zirconium is more reactive than hafnium. So, ideally, so this zirconium scavenged off silicon, right. So, and then gave a crystalline template of zirconium oxide, and then on the top of it we grew hafnium zirconium oxide on silicon, right, and you can see that this hafnium zirconium oxide is single crystalline. Okay. Now, you can maybe see that the silicon oxide is still there, right. So, this is the amorphous silicon oxide. Why? Because so silicon plus oxygen gives rise to silicon oxide, right, and then the zirconium is taking away oxygen to form zirconium oxide, right. The more of zirconium oxide is formed, this reaction starts going backward, and then silicon oxide starts reforming, right. So, this is the backward reaction. But that is okay, because by the time backward reaction is happening, I already got a zirconium oxide seed, and on the seed of, see, I first form the zirconium oxide seed, this is zirconium oxide, and so I start then growing more and more zirconium oxide, right. So, this is more and more zirconium oxide, right. So, as the concentration of zirconium oxide is increasing, this one will start going back, right. So, this one will start, silicon, this will start giving away its oxygen to silicon, and then again a silicon oxide layer will be formed here, right. So, this is the backward reaction, but that is okay, because by the time the backward reaction starts, I already started forming my crystalline template, right. So, the crystalline template is there, I already started forming my single crystal, right. So, this is how things happen, and so that is how I can get epitaxial layers of, so here it is hafnium zirconium oxide, which is what is called a ferroelectric material, right. So, it is a okay. So, and you can see from these scans that indeed I have hafnium zirconium oxide here, I have silicon, and then on and this hafnium zirconium oxide is epitaxially grown. Okay. So, same thing, right. So, if I just point out to other examples. Yeah, same thing. So here people have grown strontium titanate on silicon. Again you see this SiO2 layer, this is a reformed SiO2 layer, but the titanium is reactive enough that initially it starts forming seeds, and on the seed you start growing the strontium titanate, and then later the silicon oxide again reforms, right, and so on. Okay. So and here you see, so this is just 2 layers of strontium titanate on silicon, right. 2 layers, it is not enough for the silicon oxide to reform. So I clearly see an interface, this is silicon and this is strontium titanate, right. So here I see a clear interface because this is thin, but here I have already grown thicker layer of titanium oxide or strontium titanate, right. This is reactive enough that so as I keep growing thicker, this silicon oxide is again reformed. Okay, so but that is okay, it is again a passivating layer, it reforms, right, but I already have my film of strontium titanate, the single crystalline film of strontium titanate. Okay, so that is so these are some of the examples where such a strategy works, right. So let us go to the next slide. Yeah, okay, so this is something else, but okay, so these are some of the examples where this strategy works. Okay, all right. So with that, let us then start doing this a bit more rigorously. It is not just okay. Now as it happens, right. So okay, so I have silicon plus oxygen giving rise to silicon oxide. This is the amorphous layer of silicon oxide. This is one reaction, right, and I want the backward reaction to be so more popular, I mean so more spontaneous than the forward reaction. This is reaction 1. Reaction 2 I said is titanium plus oxide gives rise to titanium oxide. This is reaction 2. I am just going to write equal to, so that so backward and forward, so then I am not biasing you towards a forward reaction, right. But turns out there is another reaction that so that helps us, right. So silicon actually can react with oxygen to give rise to a compound called SiO, and this SiO is gaseous. That is good. So if silicon is forming a gaseous product, then that is fine, this gaseous product can go away, right. So ideally so if there are only these 2 reactions, right, so I can still make sure, right, I did not tell you this earlier, but this reaction if it exists, I can still make sure that silicon actually forms SiO gas and not really SiO2 solid. If SiO2 solid is the amorphous layer, right, but I can go to conditions where this reaction takes away the oxygen from this reaction and forms the SiO gas, and gas goes away, right, and then I still have whatever silicon is remaining is a reduced silicon, right. So this reaction I wanted to go for backward, but these 2 reactions have to go forward, right, and that can take away the oxygen from silicon and then give me the reduced silicon, right. So and with a titanium oxide seed, right. So if I am using all the 3 reactions, right. So here I have 3 reactions, right. So now things get a bit more complex, right. So I have how many species? I have 3 species, and these 3 species are silicon, oxygen, titanium, right. So I have 3 species, they are going to react with each other, and so I have 3 independent reactions, right. So I have 3 independent reactions. I have 3 species that I started with, they are silicon, titanium and oxygen, and I have compounds. How many compounds are there, right. So how many independent compounds are there? There is silicon oxide, there is so just silicon, titanium, oxygen are also compounds, individual compounds. There is silicon oxide, this is the vapor phase, there is titanium oxide, right. So 1, 2, 3, 4, 5, 6, I have 6 compounds, okay. So 6 independent compounds, right. So I have 3 independent species, right. So let's come to the number of reactions required later, but I have 3 species which can form 6 different compounds, right. So so to fit this, to solve for any sort of equilibrium, right. So I need 6 minus 3, right. So I have 6 independent compounds that can form from 3 different species. So these 3 species I at least need 3 independent reactions, right, and I do have those 3 independent reactions. The first reaction is again just to rephrase, Si plus O2 gives rise to SiO2, right. So, it is like you know 3 equations, 3 unknowns is okay, but here I have 3 constraints and you know so all are dependent. I mean so I am saying 6 independent compounds, but all are sort of dependent, they are all reacting with each other, right. So the number of degrees of freedom, this is like you know so the number of reactions are like number of degrees of freedom, right. So I have 3 species, 3 reactions, and I can have 6 different compounds that are forming, right. So 6 compounds minus 3 gives me 3, right. So this is exactly the same calculation as degrees of freedom, right. Okay, so I need 3 reactions, 3 independent reactions for me to be able to solve this problem, right. So I have 3 species and then I have 6 different compounds, and I at least need 3 independent reactions, okay. If I have only 2 species and 4 compounds, I need 2 independent reactions, okay. So like that. So Si plus O2 gives rise to SiO2, Ti plus O2 gives rise to TiO2, and the third reaction is Si plus O2 gives rise to SiO, or 2Si 2SiO, okay. So these are the 3 reactions, and so you know so I am going to so eventually I want to find the equilibrium. Right. So when I have multiple reactions, right, the first thing I want to do is, okay, so I can stare at Ellingham diagrams and all these things, that is fine, but the first thing I have to do is I have to solve them, and I have to find the equilibrium condition, right. Once I know the equilibrium conditions, the concentrations, the activities at equilibrium, then I am going to say, okay, now at equilibrium Q equal to K, right. Now how should I increase the Q? That is where the engineering comes, such that for that reaction, and here the reaction, the important reaction for us is this, the others are helping us make this reaction happen, right. So first I will find the equilibrium condition, right. So to solve these problems, the first thing I will do is find out the equilibrium, right. Once I find out the equilibrium, then I will go back to reaction 1 and say, look, what is your Q now? My Q is activity of silicon oxide. Now everything is impure, right. So silicon oxide is mixing with titanium oxide, right, and then I have, even in the metallic phase, I have silicon titanium admixture, right. So now I have impure compounds, so everything, the activities are not going to be 1, right. So I will find the activity of silicon oxide, I will find the activity of silicon, etc., and then I am going to say, look, for me to have a backward reaction, the Q should be less than the K, and K you know so at Q equal to K I know the activities, right. So then I have to increase the, or I have to reduce the oxygen pressure a bit, or I have to reduce the silicon concentration a bit, such that you know and increase the titanium concentration, right. So I am playing with titanium silicon concentrations so that the backward reaction happens, right. So first I need to find that equilibrium. Once I know that reference, then I know how to go in this way or this way, right. So let us find the reference first, okay. Let us find the equilibrium. Equilibrium is my reference. So every time I see these reactions, I do not panic. I am like, oh, Q greater than K, Q less than K, what am I doing? I am just you know confused. No, do not be confused. The first thing you do is find the equilibrium. Just close your eyes and find the equilibrium condition. Once you find the equilibrium condition, then I take a decision, right. So when I am doing my chemical vapor deposition growth or process or whatever, what are the conditions I should use? So first I will find what the equilibrium conditions are, then I move away from the equilibrium so that this reaction becomes spontaneous, okay. So then I take the decision of what is moving away from the equilibrium, but first I find the equilibrium, okay. So let us find the equilibrium here, right. So silicon oxide, titanium oxide, they form some kind of a solution, right. So both of them are impure, right. So I have you know so I have 6 compounds, means I have 6 different activities, right. So I have activity of silicon oxide, you know so the unknowns are all these things, right. So the activity of silicon oxide, when I said 6 compounds, it is their concentrations or activities or fugacities, that is what I want to find out, right. So these are 6 unknowns, 3 species, so I need at least 3 independent reactions, okay. Then I have you know so activity of titanium oxide, then I have activity of titanium, then I have activity of silicon, right. So in this titanium silicon admixture, then I have pressure, partial pressure of oxygen, and I also have partial pressure of SiO, because these two are gaseous in nature, okay. Now okay, so I can always assume, so this is what I start doing from now on, that activities are the same as concentrations because the solutions are dilute enough, or I can use this Raoult's law, Henry's law, which I didn't discuss, in a way that I can assume that so the activities are the same as concentrations, right. If they are not the same, I need to know which solution it forms, right. Is it a regular solution, or is there some other solution model where I know the relation between activity and concentration, right. But if I don't know that, I am just going to assume everything as an ideal solution, which may be wrong, right. So if it is wrong, we will know later, right. So that there is a lot of interaction between silicon oxide and titanium oxide that you cannot assume an ideal solution. But so in dilute limits there are some approximations that you can do, that mostly assuming activities as concentrations in all these reaction thermodynamics sort of works, okay. So or it puts you in the correct direction, okay. So I have XSiO2, XTiO2, XTi, XSi, right, PO2 and PSiO, these are my unknowns, right. I need to find all these values at equilibrium, okay. So that is cut short for us, right. So now I have 3 reactions. The first reaction has equilibrium constant of K1, and that is just XSiO2 by XSi times PO2, right, or so equivalently I can also write activity of SiO2 by activity of Si times PO2, right. So the fugacity of oxygen, okay. Then I have K2, which is the silicon. So this is the silicon plus oxygen gives rise to silicon oxide, that is the reaction. So K2 is silicon plus oxygen gives rise to silicon oxide, which is in the gaseous form, okay. Now K2 is PSiO, right. So this is Q, this is K, and K should be equal to Q at equilibrium, right. So divided by PSiO whole square divided by O2 times activity of Si square, or I am just going to write as XSi whole square, right, in a solid solution of SiTi in some sense, right. So that is how I am going to interpret this as, right. So SiTi solution, or in an impurity of SiTi, because Si is always contaminated with all the other impurities. So as I am just going to look at the X of Si, okay. Then K3 is equal to A or XTiO2, right, divided by XTi times PO2, and this is for the reaction Ti plus O2 gives rise to TiO2, okay. Now I have 3 independent equations, right, and I need so I have 3 equations and 6 variables, so I need 3 more equations, and those 3 more equations come from mass balance, right. Whatever be the reaction, right. So silicon is reacting with oxygen to form silicon oxide, silicon is reacting with oxygen to form SiO2, titanium is reacting with oxygen to form TiO2, right. But if I start with a given number of titanium atoms, I have to always conserve them, right. So total number of Si should be the total number of Si that I am getting from SiO, right. So that is one SiO has one Si in it, right, plus N from SiO2, that also gives one Si, and N in just pure Si or just silicon, okay. So this is 4th equation, okay. Then I have the 5th equation, which says NTi is equal to it comes from TiO2, every TiO2 has one atom of Ti, right. So if I have n atoms of TiO, n molecules of TiO2, I have n that gives rise to n atoms of Ti, so that goes into my mass conservation, plus NTi, right. So I have Ti is also an independent compound, right. So in all the compounds I am just counting the total number of titaniums, and I am saying the total number of titanium should not be more than what I initially put in all my compounds, right. Then NO, right, so is equal to 2 so from O2 I get every O2 molecule has 2 O's, right. Every SiO2 has also 2 O's, and every SiO has 1 O, right. So these 3 compounds give rise to my NO, okay. So these need to be conserved, right. So essentially so once the reactions are happening, right, so reactions are not taking new molecules or something like that, but all these things need to be conserved, and that conservation gives me. Now you may say that in growth I am actually giving new molecules, right. So but let's find equilibrium first with a given number of molecules, or I want to find the concentrations, and then to disturb that equilibrium I am going to give some new molecules of so then I am going to disturb this conservation. But for growth I am just saying that I start with n entities of titanium, I start with n entities of oxygen, these are the species, right. I start with n entities of or NO entities of oxygen, I start with n Ti entities of titanium, right, and these entities are going to react in such a way that is going to give me the equilibrium condition, right. And then I am going to say, all right, these are the concentrations required for equilibrium. Now I will use my growth chamber to say, let us disturb, let us go in a way where I am providing more concentration of silicon or more concentration of titanium, right. So let us sprinkle more titanium, so that than what is given by the equilibrium, so that so this titanium starts eating away my oxygen from silicon and silicon starts getting reduced. Then the reaction becomes a spontaneous process. That is where the kinetics comes in. But for thermodynamics I have 3 equations coming from the reactions, right. So 3 reactions and 3 from mass conservation, right. So I need to conserve mass here, okay. So once I conserve mass I am just going to have 6 equations, 6 unknowns. These K1s, K2s, K3s can be read off from my Equilibrium diagram, right. So and then I can so I can either solve it numerically, but typically that is always hard. So I can use software such as Solgas or CalFad, right, which is what it does, right. So essentially it solves for equilibrium, right. So it gives me the activities of various species or fugacities of various species or concentrations of various species at equilibrium, right. That is reaction thermodynamics. Once I know the equilibrium, then it is how do I engineer to go away from the equilibrium, okay. So I sprinkle in more titanium in this case, right, or so I go to those conditions where silicon is reacting with oxygen to give rise to more silicon oxide, the vapor of SiO, right, that goes away more and more. So silicon keeps on taking more and more oxygen, right. So if there Q is much less Q is much less than K, there is more sort of a driving force for that reaction to happen compared to the other reaction, right. So then I am doing this balance of what I need to really do, right. So to disturb this equilibrium, but first I need to calculate what the equilibrium is, okay. So what are the concentrations at equilibrium of all these various species, then I will say how do I disturb the equilibrium, right. So when I disturb the equilibrium, then I go to kinetics, okay. And that is what we will start doing from the next class onwards. We will start going into so kinetics, but before actually we do kinetics, right. So now in this example you may have seen that everything is happening at the surface, the oxidation, the reduction, right. So at interfaces and surfaces, right. So it is important for us to first understand the role of surfaces. I sort of alluded to you saying that okay, surfaces have these dangling bonds. So there is some interfacial energy that needs to go into your equations, right. So otherwise so thermodynamics is saying whether it is possible or not, but it is not saying where. So far I said silicon oxide forms this passivating layer on the surface. You could have as well asked, okay, if silicon is going to oxidize, why should it not oxidize somewhere in the middle of the wafer? Why should it oxidize at the surface, right? Surfaces are important. They attract all sort of nonsense. And so you have to use it in a nice way, right. They are the most active part of your material. So you have to use it in such a way that you grow materials on surfaces and then you use it to your advantage, okay. So before so deep diving into the kinetics, right, so that is making these reactions happen. Now it doesn't need to be only these reactions, right. So it can be a phase transition, right. So we have seen this, right. So if solid is transforming into gas or gas is transforming into solid, I need to have enough driving force. I can also write that as a chemical reaction, right. So this solid transforms to this vapor or vapor transforms to solid, right. And the delta G naughts or delta G's of that should be there should be enough driving force. The delta G should be less than 0 or the delta script G should be less than 0, right. So from now on to go into kinetics, we are going to see everything from the lens of a chemical reaction, which also means phase transitions are some kind of chemical reaction. I am just going to write vapor gives solid. Where is the equilibrium? that equilibrium is my melting point or sublimation point, but so I have to be on one side of equilibrium or the other side of equilibrium. So I can just look at this in lens of chemical reactions also, right. So from now on I am going to look at the rates of these reactions, etc., but for me to get to the rates of the reaction I need to know how far away it is from the equilibrium, right. So once I know how far it is away from the equilibrium, then that becomes easy for me to calculate the rates of the reactions, right. The forward reaction should take place more than the backward reaction. So the rate of forward reaction should be much more than rate of backward reaction. Then so within a time scale this will happen, right. So this leads to kinetics, okay. So we'll stop our thermodynamics here, the bulk thermodynamics here, right. So at this stage, and from the next class onwards we are going to develop the rest of the course towards understanding the rates of reactions or rates of processes happening, right. How fast it happens, what are the mechanisms of growing things, right. So when things are growing, how fast are they growing and how are they growing, right. So these are the questions that we need to answer, and to go there we still so are not yet there, right. So we should still understand, okay, so first of all, for me to grow something, how are they growing, how fast are they growing, but before that where are they growing? They grow typically on surfaces. So I need to understand some surface chemistries or surface thermodynamics. What are surface energies? What are surfaces first of all, right? So I'll understand that in the next module, and then so it is not just surfaces, but I can have some elasticity, right. So I am growing things on substrates, and these substrates can impose their own conditions, right, on the films or something like that. So I'll look at elasticity, I'll look at surfaces, I'll look at elasticity, and then I'll go to the real kinetics where I'm looking at time scales, I'm looking at growth, I'm looking at time scales, I'm looking at processes, how they are happening and where they are happening, and how fast they are happening, okay. So this is going to be the rest of the course in the next few lectures, okay. So we'll try to speed up from here onwards, okay. All right, so with that, thank you very much. I'll see you again in the next class, okay. So next class it's a different module, we'll go to surfaces, okay. All right, thank you.